Hi everybody, welcome back to the channel. In this video we're going to take a look at our last big rule. So if I could split up our rules, I would do something like this. I would call a big group of the rules talking about different types of functions or families of functions and how to be able to deal with their derivatives. And those are all really good, but I wouldn't classify those as kind of big rules. The big rules that I would say that we have so far, I would throw a power rule in the category of a type of function talking about a polynomial. So big rules, I would talk about the product rule and the quotient rule as being big rules that talk about not just dealing with the family of functions, but how do we deal with the derivative when we're combining different types of functions together. And this section is called the chain rule, and I'm going to throw the chain rule into that big rule category with product and quotient rules because it's not about a family of functions, it's about how do you deal with functions that are somehow combined together. So product rules and quotient rules, we know that how do we deal with functions when we're multiplying two functions together or dividing two functions. We already know that when we're adding two functions or subtracting two functions, you can just take the derivative of each of those functions separately. But in a past video, we talked about how with functions, there's really kind of 5 operations, not just 4, not just addition, subtraction, multiplication, division, but when we talk about dealing with functions, now there's actually a 5th operation as well, which is composition. And what happens when we have, so what do we do when we have f of g of x? What happens when we have one function plugged into the other? And that's what the chain rule is going to be able to deal with. So this is a really important rule. We're not going to look at as much as kind of where this rule comes from. We're really going to look at how to be able to identify when to use this rule, because I think for many students that's the hardest part, is knowing when do I need to use the chain rule. Okay, so let's go ahead and take a look at the rule, and we'll see how this is applied and how will we know when we're going to use this. So the chain rule applies when we have one function inside of another, and you could either write it as f of g like this, like we did before, or another way to write that same thing is to say f of g of x like this. And so this is going to be the case when we have one function on the outside and one function on the inside. And I think it's helpful to kind of identify them as those, using those words, an outside function and an inside function. So I don't know if you've noticed this so far, but every type of function that we've dealt with has basically just an x as the inside piece. We know how to deal with the sine of x. We know how to deal with an e to the x. We know how to deal with polynomials that just have, where you can just kind of isolate the x inside of the different terms that are there. But what we don't know how to deal with is something like this. Let's say we have something like f of x equals the square root. We know how to deal with the square root of x, but what we don't know how to deal with is something like the square root of 3x squared plus 7x, where you have a function inside of a function. Okay, or another way to another example of this is we know how to deal with the sine of x, but we don't know how to deal with the sine of x to the 5th plus 1, okay, where there's another function inside of the sine function, or in the first one there's another function inside of the square root. We know how to deal with e to the x. What we don't know how to deal with yet is e to the 7x squared plus 3, okay? So all of these have kind of a function inside of a function. And what I would recommend is getting really comfortable with recognizing, do I have a function inside of another function? And if I do, what is the outside function and what is the inside function? Okay, so let's kind of look at this first one here. I'm going to highlight this. Let's look at this on the next page. All right, tell you what, we're going to see where the derivative comes from first, and then we'll see how to be able to take the derivative of this function f of x specifically. So let's suppose that in general we have some function f that has a function g of x on the inside. Okay, so if I asked you what's the input into the f function, if I write it like this, the input into the f function doesn't look like it's an input of x, rather the input is the function g of x. So we have a function that is input into another function, and then g the input into the g function is an x. So here's another way to write the same thing. We could say we're going to have f of g, and then g deals with x. And so when we take the derivative of something that has a function inside of a function, we actually have multiple layers here that we need to be dealing with. We have an outer layer, we have an inner layer, and here's what the derivative looks like. This is the chain rule. This is going to be our important derivative rule. It says that we can take the derivative, somehow when we're taking a derivative, we need the derivative of f and we need the derivative of g to both show up. It's kind of like when we talked about a product rule, how in the product rule, when we had an f and a g working together, the derivative of f showed up in the formula, so did the derivative of g. But it wasn't, to take the derivative of a product, it wasn't just take f prime and multiply by g prime. The same thing is true here. It's not just f prime times g prime. Although there is kind of an element of that. There is going to be an f prime, I guess I shouldn't say it's not an f prime times a g prime. It kind of is. We just got to be careful about what our inputs are. The chain rule says that you can take the derivative of the outside function, which is this f, but when you think about what f has as an input, f does not have x as its input, right? We already said that f has g as its input. And so when we talk about f prime, it's not going to be f prime of x. What we need is we need to keep g as the input into that function. Okay, so we have something like f prime of g of x. So if g, the function on the inside, is originally the input into the function f, then g also has to be the input into the derivative of f. Now, let's say we have two different composition of functions, something like the square root of 3x squared plus 7 and the square root of 2x squared minus 1. The outside function for both of these is the square root function. And so what we're saying is when we take the derivative of the outside function, for both of these two functions, the derivative of the outside function is going to be exactly the same. And you just take g of x and put that in as your input. But I tell you what, the function that's on the inside, the 3x squared plus 7 or the 2x squared minus 1, whatever that function is should also impact the derivative because we want to know how that inside function is changing also. Okay, so the chain rule says you need f prime of g of x, but then we're also going to multiply by g prime. How the speed of the inside function, or I should say how the position changes, in other words, the speed of the inside function should also dictate what the derivative of the whole thing is going to look like. So we need a g prime in there. And then, oh yeah, what was the input into the g function? That was just x, right? So when we take g prime, then we need the input of the g function, which is just x. So this does take the derivatives of f prime and g prime and multiply those together, but we got to be really careful about what is the input into each function. The original input into the f function was g of x, so that's what needs to go into the derivative of f. And the inside function the input into the g function was originally an x, so the x goes into the g prime function. Okay, notice what we do not have, and this is a really important distinction because I see this as a really common mistake from a lot of people. What a lot of students want to do is they'll kind of get the idea of talking about an outside function and an inside function, but what I see, this is a really, really common mistake from students, is I see students want to do something like this and take the derivative of this and say, okay, great, that must be f prime of g prime of x. That is not true. Okay, so don't make that mistake of just saying all I need is a derivative of f and a derivative of g and just kind of put them together and I have composition, so the derivative must have composition of f prime of g prime. No, that's not true. That's not the case. Okay, we need f prime times g prime, but the input into the f prime function has to be the g of x function that was the original input into the original f function. Okay, so let's see what this means in a practical example. The first example that I wrote out earlier said, I called it f of x, but I tell you what, for the sake of not having f be confusing, I'm going to call it h of x. So h of x is the square root of 3x squared plus 7x. And the way you can think about h is that h is the composition. So h is f of g of x. And here's the way I would kind of think about this chain rule is we want to be able to deal with one layer at a time. We're going to kind of peel back an outside layer and deal with its derivative, and then we're going to move inside to the next layer and deal with its derivative. And then if there are more, because there could be more than 2 layers, we will peel back another layer and go inside one layer at a time. This always reminds me of Shrek. I like to kind of make the joke. It always reminds me of Shrek. If you've seen that movie, there's a line that says, "Ogres are like onions," right? And why are they like onions? Do they make you cry? No, ogres are like onions because they have layers. Okay, so derivatives are like ogres, which are like onions because there's layers. And the idea is you got to kind of peel back one layer at a time. So the way we're going to do that is we're going to look at the first layer, or the outermost layer of this function. Now, this is something that's going to be a really common practice for us when we're talking about derivatives. Notice at the beginning there's a square root in the problem. I'm going to change that. I don't think the square root is the easiest thing to be able to deal with. I think what would be really helpful, and I've said this multiple times already in previous videos, is that it's helpful to be able to go back and forth between fraction exponents or negative exponents and be able to deal with those. So when you have a square root, another way to write a square root is to write it as a 1/2 exponent. I think that's a little bit easier because whenever we have square roots, we're not going to deal with that derivative by using that limit definition of the derivative. What we're going to do is we're going to turn it into a 1/2 power, and then we're going to use a power rule, which is a little bit easier. Okay, so let's take a look at the outsidemost function first. It's kind of like saying that f here, and I'll just say f of parentheses. I won't even put anything in the parentheses for right now. F of parentheses is equal to parentheses raised to the 1/2 power. Okay, we want to think about that as kind of our outermost function. And then g of x as the innermost function is 3x squared plus 7x. Okay, so we want to think about remember what the chain rule looks like. It says you can take the derivative of f, but make sure that you plug in g of x as its input. I'm going to write it over here to the side again, just because we haven't seen it enough yet for that to quite sink in. But when you have f of g of x, you take its derivative, you get something like f prime of g of x, and then times g prime of x. So when we're looking for h prime down here, we want to know what is the derivative of the outermost function. What is the derivative of f? Okay, now hopefully this kind of makes sense of why I put just parentheses to the 1/2. Because when we find f prime, that's going to look like 1/2 times parentheses raised to the negative 1/2. Okay, so that's the derivative of the function something to the 1/2. Now the question is, what goes inside the parentheses? Okay, is it 1/2 x to the negative 1/2? No, it's not, because if you look at what was originally inside of the f function, it wasn't just an x, it was the entire thing g of x. And so the chain rule says don't just copy and paste x, and don't put a g prime inside of the parentheses. What you need to put into the parentheses is just copy and paste whatever g was. So this looks like 3x squared plus 7x goes inside. This part right here is our f prime of g of x part. Okay, so you should have a derivative of the outside function, that's the 1/2 times something to the negative 1/2, and you should have just copied and pasted g of x and put that in the inside. Okay, now we also need to multiply by g prime of x. So g prime of x is the derivative of whatever was the inside function, and this is why I think it can be helpful to write out kind of f and g at the beginning. The derivative of the inside function, that's a power rule, and again, hopefully you've been practicing your power rule enough that you're comfortable with this, but this is 6x plus 7. Okay, so we have f prime of g of x, and then this last part on the end right here, this is g prime of x.